the work done by a constant force or a constant net force. We say a force acting on an object over some distance d does positive work on the object. Capital W will represent work, so capital W, work greater than 0. If the force pushes roughly with the motion, that is an acute angle between net force and the velocity, the direction of motion, and therefore tends to cause the object to speed up. So positive work causing the object to speed up. We say a force acting on an object over a distance d does negative work on the object, work W less than 0, if the force pushes roughly against the motion. There's an obtuse angle between force and velocity, and therefore tends to cause the object to slow down. So we call this positive work, we call this negative work. We say a force acting on an object over a distance does 0 work on the object, W is 0, if the force pushes at a right angle to the motion, 90 degrees there between net force and velocity, therefore tending to cause the object to maintain its speed, neither speed up nor slow down. So this concept of work is going to be a scalar, not a vector. It's just a number that quantifies how much the object speeds up or slows down over some interval due to the action of a force. The amount of work done determines how much the object will speed up or slow down. And the amount of work depends on 3 factors. One, how strong the force is. Stronger force is going to do more work. How far the object travels. So the further the force pushes the object, the more work is going to be done. And then that angle between force and velocity, or average velocity, or the displacement. That angle is going to determine how effectively that force was able to do work over that distance. And there are 2 different but equivalent formulas for computing what we call the work done by a constant force or a constant net force. So 2 formulas that take these 3 factors into account. I'm going to introduce those 2 formulas. Using this scenario, so suppose our dwarf miner here tosses his gem on a windy day outside, tossing it straight up, but the wind carries the gem off to the right here. So we have a moment 1, a moment 2, and a path the gem followed in between. We want to look at the work done by the force on the gem from the wind, and also the force on the gem by gravity as the gem moved along that path from 1 to 2. Formula number 2 will be the formula we discuss first. So here's an introduction to formula 2 for computing the work done by a net force. We're going to draw the displacement vector pointing from moment 1 to 2 and look at a free body diagram for our gem between those 2 moments. We're going to assume that it's a constant force of gravity, and we're going to assume that the force from the wind pushing the gem to the right is a constant drag force to the right. Now, that's not very accurate. Forces of drag tend to vary as the object changes speed, but for simplicity here, we'll assume a constant drag force to the right. So there's our free body diagram, and with our tail-to-tail rule for summing vectors, we can find the net force pointing down and to the right here. There's our net force vector, sort of following our parallelogram rule for adding vectors, down and to the right. So we'll assume that's constant from moment 1 to 2. Now let's put some numbers to it. Breaking up that displacement vector into components, suppose we have this horizontal displacement, delta x, this vertical displacement, delta y, so plus 8 meters this way, but a negative 2 meters. That's our vertical displacement, delta y. And then we'll give these values for our force components. The net force in the x direction, 3 newtons to the right, and then negative 4 newtons pushing down there. So that's negative 4 newtons from gravity down and positive 3 newtons from the wind to the right. Here's our formula. The work done by a constant net force, in this case, or constant force, it works either way, can be found by taking the sum of the products of the parallel parts. That is the x component of the force times the x component of the displacement, and add that to the y component of the force times the y component of the displacement. So we're multiplying forces times displacements here, or forces times distances, forces in newtons times displacements in meters. So our unit here is newtons times meters, or Newton meters. Newton meters is our unit for work. So in this case, the net work can be found from the same formula. We're just going to replace Fx with the net Fx to find net work, and Fy with net Fy to find net work. So our net Fx times the delta x, add that to our net Fy times delta y. Note here that the signs do matter. The x component of the force and delta x both pointed to the right, so they're both positive, the 3 newtons and the 8 meters. Our drag force pushing to the right, while the object also moved to the right. Drag force was pushing in the direction the object traveled. In the y direction, the y component of the net force was pushing down, and the displacement was also down. So this negative Fy and also a negative delta y, multiplying them together, we get a positive value. So overall, our net force was pushing roughly with our displacement, so it does positive work to speed the object up. So we sum this value with this value to get 32 Newton meters, and we'll call it the positive, we'll call that the positive net work done on the object by the net force. And the fact that it came out to be a positive number, that indicates that the final speed will be greater than the initial speed. Our gem will have sped up from the moment it left the miner's hand till this moment down here shortly before it hits the ground. So that's formula number 2. Now I'll show you what we'll usually call formula number 1. We will be able to get the same result just from a slightly different perspective. The other perspective is to look at the magnitudes of those two vectors and the angle between them, rather than looking at components. So let's say here that the magnitude of our displacement vector can be found from the components we already know using Pythagorean theorem. So there's the magnitude of delta r. We can also get the magnitude of the net force from the components we already know. And I'll give you the angle between those two vectors. Let's say it's 39 degrees. With these pieces of information, which mirror these 3 factors mentioned above, strength of the force, how far we traveled, and the angle between force and displacement. With those 3 pieces of information, we can compute the work using this formula, what we'll usually call formula 1. Work done by a constant force or a constant net force. We take the magnitude of the net force, multiply it by the magnitude of the displacement, and multiply that by the cosine of that angle between them. Note here that since magnitudes of vectors are always non-negative, so 0 or positive, it is the angle that's going to determine whether this work is positive, negative, or 0. Cosine of the angle can be positive, negative, or 0. That's going to determine whether the work done is positive, negative, or 0. So plugging in our values for the net force, for the magnitude of the net force, the magnitude of the displacement, and the cosine of the angle between them. That is an acute angle, so the cosine of it will be a positive number, so our net work comes out to be a positive number. Note 32 Newton meters, the same value we got from the other formula. The 2 formulas will give us the same result. And that positive net work done on the object indicates that the object will be faster at moment 2 than it was at moment 1. So we'll be able to use either of these formulas in the scenarios we encounter to find work. The formula we choose just depends on the information we have. If we happen to have the components of the forces and of the net force and displacement, then we'll use this formula. If we happen to have magnitudes and angles, then it's more convenient to use this formula here. All right, time for you to practice. Here's a scenario where an object starts here at moment 1, travels along this curving path to this location here at moment 2. Assume that it's subject to a net force that points like so the whole time. Assume it's a constant net force along this whole path. There's our displacement vector from 1 to 2. I've shown a 40-degree angle between net force and the horizontal and call this theta here, our angle between net force and displacement, and there's some other unknown angle phi right in there. So with this given information, I would like you to compute the net work done on the object between moments 1 and 2, first using formula number 2. And a hint, to do that, you're going to need to do some trigonometry to break that net force vector into components. You know the net force magnitude, and you know that angle 40 degrees there. Use that to break net force into components, and use those components in formula 2 to get the net work done on the object between those moments. Next, check that answer by using formula 1. Here now, you're going to need to use trigonometry to calculate angle phi, so that once you know what angle phi is, you can add it to that 40-degree angle to find angle theta there, since you'll need this magnitude, and that angle to use formula 1. And your result should agree with what you got from A. And then last, I would like you to just sketch vector v2 at moment 2 on this diagram, thinking about what direction that velocity vector should point and how big it should be compared to v1. So once you know the net work from your answers to A and B, that should help you determine how velocity at moment 2 should compare to the velocity at moment 1. All right, so you're going to pause the video in a moment and perform those tests. Pause the video. All right, ready? Here's our answers. To use formula number 2, you're first going to need to break that displacement vector into components. So doing some trig here, we'll get the force broken into components first, actually. This force, using sine and cosine of that 40-degree angle to get the net force x component and net force y component. Those are both negative since we're pushing in to the left and also pushing down. So both negative components there. That sign is crucial. And then once we have those components and we know delta x and delta y, since those were given, we'll use the formula here. So negative and negative makes a positive value, and then negative and positive makes a negative value here. The overall result comes out to be positive. But getting those signs right is crucial. The sign indicates the direction, left versus right, up versus down. So 43 Newton meters is our answer. Note that it's a positive number. We're going to test that by using the other formula now. We'll need to find angle phi. We'll do some trig here, given delta x and delta y, to find that angle, add that angle to 40 degrees to get 70 degrees. So we concluded that this is a 70-degree angle there. It is still an acute angle. So we expect that the net work is going to be positive because of that acute angle between those two vectors there. So using formula 1, with the magnitude of our displacement vector, magnitude net force times magnitude of displacement times the cosine of the angle between them. That's the cosine of the 70-degree angle. And we get about 43 Newton meters in agreement with the other formula. Lastly, vector v2, the velocity at moment 2, what you should draw should be a vector that is tangent to the path at that moment, since your velocity vector is always tangent to the path at any given moment, and its length should be greater than the length at v1, since the net work was positive, indicating the object is faster at moment 2 than at moment 1. We see again here how the velocity vector turns over time. Initially is pointing up and to the right, but over time it turns and tilts to be pointing down and to the left, aligning itself with that net force vector and therefore the acceleration vector over time.